Good afternoon, everyone. How are you guys doing? Good. Who went to the lab today? How was that? Did it work? Did you hear a loud bang when you crashed the sample? Probably, you know, that might be a little bit scary, but as long as you put a shield around and you have your safety glasses and you don't have your finger in there, it should be fine, okay? So don't worry about that. Why is there a bang? You're gonna hear the bang when you do the lab. But why do you hear that loud noise whenever the rock breaks? Where does it come from?
The potential energy that was stored in the rock.
Exactly, right? It's the strain energy in the rock, or elastic energy in the rock. When you compress it, you apply a lot of force. You can't see how it deforms, but it's taking a lot of energy. When that energy is released, it makes that noise. And it's a similar thing what we're going to see later on with acoustic emission, a microseismicity that is used to measure how far hydraulic fractures go. And those also use that principle. Whenever the rock breaks, releases elastic energy, and you can measure it with geophones in order to say where the rock broke for hydraulic fracture. So, yes, sir.
So you said you were going to explain why it fractures at an angle.
I say what?
Why it fractures at an angle? Why does it do that? Why does it?
Oh, okay. But that's we're not quite there yet. That's going to be next week when we talk about rock failure. We have to see a few more things before we get there. But I'll get there. Hopefully, also you saw that the rocks fracture at an angle, steep angle, and sometimes it's more or less vertical, but some other times it's at an angle, and we'll see that later on. That's related to shear failure. I wanted to tell you as well that I had forgotten to add this, but now it is there. Homework number 3, due in 2 days. Remember, it's just problem summer 1 and 2 for this week. But if you did all the problems, then that's good, because next week you have to turn in 3 to 5, okay? So don't worry about that if you completed that. Okay, so let's continue with the lectures. And let me switch over here. So last class we learned that we could use these equations of linear elasticity in order to tell what is the horizontal stress whenever there are no strains from the sides. And using those equations, we derive this very important equation that tells us what is the horizontal stress as a function of the effective vertical stress and as a function of the Poisson ratio. Okay, so what I'm going to do now is to extend these equations to consider the case when there are tectonic strains. In this case, remember we said that there are no tectonic strains. So epsilon 1, epsilon 2 is equal to 0. This is what is usually called a tectonically passive environment. And also we derive the formulas to calculate the fracture gradient. We'll come back to this later on when we talk about hydraulic fracture, don't worry. I don't have white pages. Anyone has paper? Unruled? Yeah? Okay, I got it.
Oh, yeah,
Thank you very much. Okay, I got it.
Extra points.
Extra point. Yes. Last night.
See ya.
I'm kidding. You have to earn your extra points for answering questions. Okay. So let's say that now we are at some place where there are mountains, and there is a sedimentary basin in this location, and there are significant now stresses that come to the side. Because we said that the tectonic plates, they move, because they move, now you have all of these stresses, horizontal stresses, that are going to be different than what you will have at repose with no tectonic stresses. We're going to call those tectonic stresses with epsilon, and we'll have two. One, we're going to call it the maximum tectonic stress in horizontal direction, and there is going to be another one perpendicular to this one that we'll call a minimum tectonic stress. So I'm just going to copy the equations here, but if you like math, you can do this at home, and it's not too difficult. All I'm going to do here is now to take these strains. Let me add here a coordinate system. Let's say this is 1, this is 2, and this is 3. Epsilon 1, and epsilon 2 are not going to be 0 anymore. Now they're going to have a finite value. And I can use all of these equations, and I will find out that the solution for that is that sigma 1, sigma 2, and sigma 3, now they're going to be all functions of the tectonic strains and the effective vertical stress. And this is going to look like this. Again, I'm just writing the worked out equations. I repeat, you can do those at home if you feel like doing that. Sometimes Friday night I do that. Just derive equations, not so fun. So notice, this is the first equation. This is strain 1, strain 2, and the vertical effective stress sigma 3. For sigma 2, it looks similar. And I have this one over here, and sigma 3 is just going to be the value that you calculate from, let me find my eraser. Looks like I have to borrow an eraser too. Wait a minute, I borrowed an eraser actually. Oh, here. And sigma 3 is a value that we know, and it's going to be SV, and if we want to do it general, we could do this, bulk G dz minus the pore pressure. That's going to be sigma 3. So let's try to analyze these equations. Notice that if I don't have tectonic strains, if these were to be 0, then we will recover what we had before, and sigma 1 will be equal to sigma 2 and just equal to that. This is the same as we got before. But if we have additional strains because the plates are pushing in this direction, my effective horizontal stress is going to be larger. How much larger? It depends on how big is that tectonic strain, and also depends on the stiffness of the rock. the stiffer the rock, the bigger the young modulus, the higher is going to be that horizontal stress. And notice that also is going to depend on the Poisson ratio. For example, in this case, if we look at sigma 11 and epsilon 11, there is a direct relationship between sigma 11 and epsilon 11 through this entire coefficient, which is called E prime, and it's called the constraint. No, sorry, it's not called constraint. The other one was called constraint. This one is the plane strain modulus. You remember that I told you that Young modulus and Poisson ratio are useful quantities, but those are not what we usually need in the subsurface. In the subsurface, we'll have different proportionality factors because we are under confined conditions. And in this case, is a plane strain modulus, which depends on both the Young modulus and the Poisson ratio. And if you remember a few lectures, or last lecture, we saw that we have the constraint modulus that also depends on the Young modulus and the Poisson ratio. But usually we do not have unconfined loading in the subsurface. So it's a combination of many of these. Okay, so let's now make this one one step simpler and related to the epsilon h max and epsilon h min. In which direction am I going to have the maximum horizontal stress? In the direction of epsilon h max or in the direction of epsilon h min?
H max.
In the direction of h max, right? So this is going to be equal to epsilon h max in direction 1 is going to be 1 minus this, directly proportional to epsilon h max plus this one, which is proportional to epsilon h min, but not is proportional through the Poisson ratio. The Poisson ratio goes from 0 to 0.5, usually 0.2, so it's just 20% of that effect of in the perpendicular direction is going to go into the perpendicular direction, h max from sigma h min, plus what we have due to vertical stress. And sigma h min is going to be also affected by epsilon h max, but just a little bit, and it's going to be directly proportional to sigma h min through the plane strain modulus and the vertical stress. Okay, so now with this equation, we can tell what are the two horizontal stresses at this particular location, given the fact that we know the vertical stress, something that we can calculate, and these two so-called tectonic strains. And also that we know the Young modulus and the Poisson ratio of the formation. How would you get the Young modulus and Poisson ratio of the formation as a function of depth? So this one we know how to get it, okay? Just that equation, we know how to do that. And let's assume that we also know pore pressure. This one, we know it. What about Poisson ratio and Young modulus? How do we get those?
Ratio of strain.
Okay, but usually in the field, we're gonna need a continuous measurement as a function of depth. So that's gonna come as a combination of well logging files or well logging surveys, particularly slowness, delta TP for the compression wave, and delta TS for the shear wave, with a combination of laboratory tests, what you're doing in the lab. We're going to see why we need these two, we need those two. Sometimes with just a well login, we cannot get everything that we need. But there is something missing, right? And that something missing are the tectonic strengths. How would you get the tectonic strength? Is that something that you can go and measure in the field? Short answer is no, it's not something that you can measure directly, right? But how can you get it? If we use this model, and I'm telling you this is used a lot in order to build models of stress expansion of depth. How would you estimate these two?
Could you get H max and H min through something else and then work backwards?
Exactly, that's what you do. So you measure these two at some points, not everywhere, because it cannot be measured everywhere. You can measure these, we're going to see later with wellbore failure, and also with hydraulic fracturing tests. So you can measure those two, and then the tectonic strength is something that you calibrate, and you get to know what their value is based on those measurements. And once you know that those tectonic strengths, they more or less fit well the data that you see in the field, then you can be comfortable to extrapolate these to some other depths. That's how usually you do this calculation of tectonic strengths. Once you do that, you can calculate everywhere what are these stresses. And we're going to see later on that that's very important, because that's what sometimes adds something which is called mechanical stratigraphy. For example, here you could have a very stiff carbonate, and here a soft sand, and again another carbonate. If the carbonate is stiffer, usually it's going to build up more stress than the sand. We're going to see that later on. Don't worry about that right now.